So let me share my screen again. Okay, so you should be able to see my screen. This case, we're moving on to a different type of modeling problem. It's shorter. This lecture is shorter because it can be, because last lecture we talked about 3 different classifiers. We talked about naive Bayes classification and decision trees. We also covered cross-validation for logistic regression. So there's quite a bit of content in the last lecture to go over. This lecture, we're only talking about one model, and that's a clustering model called k-means. And so it's going to be a bit more focused and I think more intuitive in terms of the way that it's described, less math. So it should be perhaps a break from the more intense lecture last time. Okay, so the title is, can we detect patterns among specific customers to identify potential fraud? So you could think of that as a classification problem. If you know the answer, you have information about different customers, and then you have the result that you learned of whether they were fraudulent or not. So you could think of this as a classification problem where you build a model, and then given information about a future customer, you want to predict whether they will be they will commit fraud or not. So it's naturally a classification problem. We're going to look at it in a different way, where we don't know the answers about any of the customers. We're going to look at a situation where we have information about customers, but we don't know the truth about whether they committed fraud or not, or whether there was fraud involved in the customer transaction. We're going to do that by just looking at the features themselves. So rather than using the features to try to predict an outcome, we're just going to look at the features by themselves, and rather than doing, say, an exploratory data analysis approach, we're going to try to build a model on those features to see what things look normal, what things look abnormal, and if our model can somehow tell us about those things. And so we won't be giving an answer to whether somebody's committing fraud or not. We're looking for outliers or unusual things that perhaps a human could then look into. So the problem is allows us to talk about a specific model called k-means as a clustering algorithm, which is the main purpose of this lecture, to cover this model, to describe the clustering problem, to make it clear what this is doing. Specifically, we're going to learn about the algorithm behind k-means to also try to understand when it works and when it doesn't. During this case study, we're going to perform exploratory data analysis on the data set that we're working with in order to observe natural clustering within the data. We'll then introduce k-means as a way to automatically determine clusters in the data. So rather than looking at the data with your eyes and trying to determine how many different groups should I split this data set into, we're going to discuss an algorithm that can do that for you. We'll then implement and fine-tune the algorithm to validate our findings, because being able to kind of understand what's going on with an algorithm is crucial for a data scientist. So the introduction in the business context that we're looking at in this lecture, we're pretending like we're working with a fraud team at a large insurance company that deals with issuing insurance policies for various types of claims, both for individuals and businesses. Policies which are issued are kept track of, and any files claimed are examined and then evaluated to determine whether they're legitimate files, and then you would then approve those to pay out the claim. So somebody gets into an accident of some type and they need the insurance to help pay, they file the claim, and then the insurance either approves it or doesn't approve it. But there are also instances, I think like the credit cards from the previous example, they're very rare, so we're talking about a small fraction. But there are instances where individuals will try to claim an injury or something like this to get money from the insurance company. That's just not true. They'll take advantage of it, or perhaps they'll value or overvalue something, many times more what it's actually valued or something like this. So the role of the fraud team is to determine or to try to determine which claims should be approved and which should be denied. And they could be denied for fraud, or they could be denied for legitimate reasons, because not every insurance claim is approved. Sometimes, but whether you should approve or deny for a claim. The business problem is that we want to answer the following question: are there particular patterns in the groups of filed claims that may be indicative of fraud? So we're not going to answer the question completely. We're not going to come up with a final model for making these decisions, because that would be a classification problem. We're interested in looking at the data to see if there are patterns that seem perhaps unusual, groups of data that seem, parts of the data that seem unusual. The context is that the accounting team at this place we're working with has provided us with data on recent claims made by 1,000 individuals. So we have 1,000 data points. And unlike the previous examples that we've looked at, this data is not labeled. What that means is there's no corresponding result or output for each data point that we're trying to predict, like, is it fraud or not? So we don't have that information. It's unlabeled data. As a result, we can't use classification models. So you can't use a classification model to predict the outcome of something if you don't have data that gives you examples of those outcomes. So instead, what we're going to look at is a clustering model called k-means, which allows us to do what's called unsupervised learning. So supervised learning is where the model has access to both the input and an output, and then the model tries to learn how to predict the output based on the input. That's supervised learning. Unsupervised learning is, you could think of it as almost, you just have inputs. There's no output you're trying to predict. You just have inputs, but now you want to somehow understand that data through some model in order to get some insights. But there's no correct answer. It's more like a model-driven EDA. So this case is structured as follows. First, we're going to perform exploratory data analysis to visually investigate the structure of the data that we have. We're going to then use those observations to help guide our clustering methodology that we're going to use and learn the models. We'll then discuss the advantage and limitation of these types of clustering models we're going to talk about. And then we're going to actually cluster the data, generate some potential conclusions for particular clusters of data. Okay, so we read in, we load everything up, we import all of our data, and we look at the first 5 rows of our data set. And this is what we're dealing with in our data. So we have 7 columns. The first column is just an ID of the person, so that's not really useful for us. The second column is the income of the person. So I should say each row here is a claim made by somebody to an insurance company. They say, I want you to give me this money because something happened. So the second column contains the income of the person filing the claim, how much money they make. The third column shows the age. The fourth column shows the sex. The fifth column gives the result of whether the insurance company approved or denied the claim. So this is actually the label. You could use this as a label for building a classifier, but we're not going to build a classifier, so that means that this information is going to be ignored for us. But this is the actual result of whether they approved it or denied it. So that's a label of whether they approved or denied it. The fifth column then tells you, or sixth column tells you whether there was actual fraud or not. So there's, this is not something that we're going to be using, but it's useful to kind of know what kind of data sets are out there, so we can still talk about it. So this is saying whether or not there was fraud. So some of them you have approved and there was no fraud. Some you have it was approved and now they're under review. They're reviewing whether fraud took place. Some of them, I don't know how they get this information, but it's denied and they don't think there's fraud. Maybe their policy just did not cover what was being, their policy didn't cover the thing they were trying to get money for. It was for one car and they wanted the money for a different car or something. And then there's denied and fraud. And I assume maybe there was some investigation prior to denying them and they found out it was fraud. I don't know. But this is information we're not going to use, but you could imagine that there would be kind of almost two labels that you could build a classifier on, whether you should approve or deny somebody, but then you also need to know, do you think it's fraud or not? You could deny somebody the loan, the insurance claim while they're not being fraudulent. So they're kind of two different levels of what you might want to predict. And then finally, this is the interesting column for us. How much did they want? So they made a claim and this person asked for $9,500. This person asked for $19,000 and so on. So this is how much they claimed. So for our particular problem, we're going to focus in on just these three columns. Case ID is still there, but really just these three columns we care about. How much they make, how old they are, and how much they're trying to get. Supervised and semi-supervised learning. So yeah, I can just give a brief. So semi-supervised learning. So it's useful to know this, so I should answer this. Semi-supervised learning is where you want to do supervised learning. You want to build a classifier, but you only have the labels for a subset of your data. So maybe you have 1,000 data points. You have labels for 500 of them, but then the other 500 you don't have any. You don't have the result. So if you built a supervised classifier, you would throw away 500 data points and just keep the 500 that you have the labels for. Unsupervised is throw away the 500 labeled data points and just look at the 500 without labels and then try to understand that. What semi-supervised learning is it's a different framework with different models, but the problem is related. You want to build a classifier using the 500 labeled data points you have, but you think that the structure of the features of the unlabeled 500 can give you information about the data. So if you think of your 1,000 data points in this example as living in some space, like a cloud of data, you think that the entire 1,000 data set points all has information about what statistical properties the model has, the data has. You just only have labels for half of them. And so it's a model that uses the information from all 1,000 data points, but then only predicts based off of 500. So it's kind of, the techniques are pretty different from everything that we've been talking about. But the problem is basically that. So unsupervised learning, I would say, is descriptive. It's you're trying to kind of understand what's going on with your data. So in that sense, the models can become more kind of creative, and you're just trying to tease out information in the data. Okay, so this is the data that we're looking at here. 1,000 data points. Each data point is three values: income, age, and how much they want, their claim. So now let's look at this. So let's take a look at the set of claims under review and how they're distributed. So first we show a histogram of all of the claims, and we get something that looks like this. So you get kind of, it looks like 3 clusters of claims. You get a cluster of claims around 30,000, a cluster around 20,000, and a cluster around 10,000. And then, something down here, I guess at 5,000, maybe this cluster is a bit weird, something at 5,000. Why 5,000? I mean, maybe there's a minimum amount that the insurance company is you're allowed to claim. They won't pay anything less than 5,000 because that's how the policy is, perhaps. You would have to know something about the data to know if there's something meaningful kind of in this pattern. But it's a strange distribution. It seems like there are 3 different kind of groups. A single Gaussian is not going to fit this data, which is, this would be the mean of the data. This is the standard deviation of the data. So it's a strange distribution. But we're only looking at one variable in our data. We're looking at the claims, how much they claimed. So now let's look at 2 variables together, 2 dimensions together in our data. Let's look at the claims, how much they want versus their income. And also let's look at their income versus the age in order to understand what's going on. So here's the second set of plots that we're doing for our EDA. So here you see income, how much money they make, and their claim, how much they're asking for. So each dot is a data point. This person makes about $50,000 a year and claimed or wanted a little over $40,000 for some reason from the insurance company. We can do the same thing with age versus income. I guess we're showing in this one age versus income. So this is income now. This is age. You can see the age is a bit, I guess age is under 10 years old. So I would assume that somehow a parent had got insurance for a child, and the parent is claiming something for the child, up to almost 100 years old. But you get clusters here as well. I think we're going to return to talking about these clusters, but this is, so I won't go into too much detail now. But this is what the data looks like. We have 3 dimensions. We're plotting in 2 dimensions. So these 2 dimensions and these 2 dimensions. Here's how it clusters. But you might look at it and think, it looks like there are 4 groups, kind of in general, perhaps, of data. There's this group here, there's a group down here, group here, and a group here. We can also stratify by gender. Notice that we didn't include male, female in the original data set. And the reason is if you wanted to stratify and see what's going on in these 2 plots, whether they're male, blue, or female, orange, it looks like they're totally overlapped. So there's really no difference between the claims from people who are male versus female. The statistics or the distribution of the data looks the same. So we can ignore that information. Okay, so what patterns do we notice in these plots? So I'll look at the plots as we kind of notice these patterns. First, there's 4 clear patterns, I would say. And one thing you might want to do is to interpret what they might mean. So for example, here you have a bunch of claims at about 5,000. And it's kind of, the income is above a certain amount, and so what does that mean? Well, 5,000 might be, it's hard to tell. I mean, you could try to tell a story. You'd probably be as good at telling a story to yourself as I could be. So let's move down here and see what some of these stories are. So there's some clear clustering in our data. For example, there's a big cluster around the 30 to 40,000 income range. which could be due to the fact that that's what the median income is. So most people make around that according to this data set. There's also a strip of claims between 50 and 100,000, this strip right here. So there's a big group right there. You could consider perhaps that's just the average person. That's a typical thing. But then there's a strip down here of people making a bit more than average and also claiming less. They're claiming roughly 5,000. So why is that the case? I'm not sure. It could be that, I mean, here's one possible explanation, that these people are more affluent, so they have more toys. Maybe they have more cars, they have more toys they're insuring. They have a nice jet ski or something, I don't know. And so there are more smaller things that they could claim. But ultimately, we're just making up stories in our head. Ultimately, if you were doing this job, you would know about your data, right? You would know why these things are happening. There's also a strip of claims of people making only about 10,000, so small incomes, who are claiming much more than their yearly income. Right? So they're making 10,000 and they're claiming something that's much more than what they have. In some cases it's a little bit, it's like 3 times more than they make in a year. So, you might think that that's unusual or anomalous, and that might be where the fraud is. And of course, if a person buys a car, this is roughly what a car might cost, and they could have a loan that they're paying, but then the car really gets hurt, broken or something, and so they need to use the insurance to pay their car. So there are certainly like legitimate reasons why a person could be claiming much more than a low-income person could be claiming much more than they make, considering that, if they wanted a car that's new, they perhaps took out a loan, and 10-year loan, and they got a car for $25,000. That's possible, but then there was a bad accident or something. But there is this pattern to notice, and also there's this pattern here, which is kind of mimics this pattern, except it's more in the 50,000 range. So who knows what's going on there. So those are some of the patterns that we see. So there are many things that you could want to do with this data. We talked about how the data has enough information in it that we could build a classifier on it. But right now, we're just going to focus on one thing we might do with this data, which is to build an algorithm that finds clusters of our data. So if we look at this plot, of course, these are 2 plots of the same data set from different perspectives. In both cases, it looks like there are 4 groups of data, 4 what you would call clusters. There's a cluster here, a cluster here, a cluster here. So a claim is what the customer asks for from the insurance. So they say, I was in an accident and my car, I have to get a new car. My car was worth $25,000. Could you give me $25,000 so I can buy a new car? Because that's, I'm insured, right? So that's what they're doing. So what we've been talking about is kind of clustering, basically. What groups of data how does our data naturally group? But we've been doing it by eye. We've been visualizing it. And then what you could do is you could manually, by hand, go into the code and then say, okay, this is, all this data is one cluster. All this data is a different cluster, a third cluster, and a 4th cluster, right? You could manually go in and do that based off of your eye. However, in most problems, it's not going to look this clear. First, you'll have many more dimensions. So here you have 3 dimensions. You could visualize this in 3 dimensions and see that there are 4 clusters, but even in 2 dimensions, you can kind of perhaps map some of these clusters. This cluster maps to that cluster, and so on. This cluster probably, actually, this is income, so maybe this cluster maps to this cluster, I'm not sure. But you could eyeball it. The whole point is that in practice, you have higher dimensionality, and you can actually look at it with your eyes to see. So is there a way of using an algorithm to automatically cluster the data for you? So we want to take our data points and, for example, split it into 4 different groups, where each data point within a group is somehow similar to all the other data points in that group. And 2 data points in different groups are different from each other. And we want to automatically do that with an algorithm. So it'll tell you, this is the first group, and here are all the data points in that group. And here's the second group and all the data points in that group, without us having to do that ourselves, right? So we want to automate that process. That's the clustering problem in general. So there are a few different ways you can do clustering. That's the problem for all those different algorithms. It's the same problem. You want to partition your data into groups of data, into subgroups, where somehow each subgroup belongs together. So we're going to look at by far the most famous one, and the most common one called k-means clustering. And so that's going to be the algorithm that we focus on in this lecture. Okay. So in the visualizations above, there seem to exist distinct populations of individuals based on the relationships between their claims and their income and their age. So there seems to be some relationship between claim, income, and age that allows people to group into different kind of cohorts. However, we've only managed to investigate 2 relationships this way. And in larger data with many features, doing so manually would be difficult and time consuming. So if you had 100 features or 20 features, you could do all pairs. First of all, you can't visualize 20 dimensions. You could plot all pairs, the first dimension and the second dimension and the third dimension. You can plot those pairs and perhaps see some patterns. But the patterns between any 2 dimensions, it's hard to generalize those to all 20 dimensions. So maybe in a particular 2 dimensions, you have clearly 3 different groups. But does that mean there are 3 groups in the entire data set? Or if you extended that into higher dimensions, maybe that would be, those 3 groups would actually represent more groups. Like each group would be split into 2 different groups across different dimensions, right? So the problem is you can't necessarily do this clustering by hand with a lot of data in high dimensions. So there are many ways to do this, but we're going to look at the k-means clustering algorithm, which is the most common one. What it does is it partitions the data into k different groups. So k is the number of groups that you want to partition it. You could set k equal to 3, k equal to 4, k equal to however many groups you want. K is just the number of groups. And it does that in a way that tries to minimize the sum of the distances between data points in each group. So it's a bit more specific than that, what it's trying to minimize, but the high level is you could imagine that in each group, it's trying to make it so that the distances between all the data points in that group is small. So there's 3 basic steps that we follow when we do the k-means algorithm. So what is this algorithm? What does the algorithm look like? How do we run this algorithm? The first step is the initialization. We have to, so the algorithm is going to, if there are k groups, the algorithm will be characterized by k different points in the space of the data. These are going to be called centroids. To start, we have to initialize what these k points are. You could think of it as you have your landscape of all of your data, and you have k different flags, and you want to put those flags, those k flags, kind of marking different regions of your data. Yeah, so, you could think of it like that. And so we need to learn those where to put those k flags, if you like that analogy. So the first step is we have to initialize them, which is not, obvious how to do, actually. The second step in the algorithm, so then the second and the third step in this algorithm iterate back and forth between each other. So the first step initializes where the K centroids are. I won't keep saying flags, but you can think of them like the flags. Then the second and the third step iterate back and forth until the algorithm converges. The second step is to assign each data point to one of the K groups. And the way that it does that is for each data point, you calculate its Euclidean distance. How far is it to each of the K centroids? And then you assign it to the centroid that it's closest to. Right, so there are K different points, centroids in this space, K different flags, and you want to assign each data point to one of those K groups. You assign it to the one that it's closest to according to, really you could do any distance that's meaningful. Euclidean distance is the default when you run K-means, but there might be different distances that are better. But Euclidean is the meaningful one. So yeah, Euclidean, there are two reasons for Euclidean. First is it's the line of sight, which people like intuitively. It's just, being humans, we like that. How far am I? If I wanted to walk directly to a location, how far is it? The more kind of in terms of machine learning, the algorithm, the bigger reason is it's the math works out really nicely. So you can take derivatives set to 0. So the algorithm, to optimize the algorithm, it's very simple. Whereas if you use different distances, the algorithm, usually it would be more complex. So the default algorithm is the simplest one, which is Euclidean distance. So there's no proof that the algorithm converges to the optimal solution, but it does converge just to potentially a local optimal. So I'll probably return to that. So there are other distances that you can use. The other one is called the Manhattan distance. It's this like the city distance. If you have a city, Manhattan, the streets are like a grid, right? So you can't walk through buildings. You have to walk, in one of two directions, east, west, or north, south. And so that's that would relate to the L1 distance. That might be the distance you choose because of the problem. But there are many distances. If you're clustering text or signals, there are other distances for that. But we're just focusing on the Euclidean distance. So the features, the assumption that we're going to return to is the main assumption is that they have to scale. All the features have, first of all, we're assuming that the features, this is key, can be modeled as continuous valued. So that's crucial. If you're calculating a distance and one of the features tells you what country you're located in, right? Well, okay, that's a bad example because you can give geographic locations. But if you think of the previous one, there's the verified, the previous example, it's verified, semi-verified, and not verified, right? So those are the three options. How do you calculate the distance between those? You can't. What's the Euclidean distance between somebody who's verified and somebody who's self-verified? So it has to be, for the Euclidean distance, it has to be meaningful to take Euclidean distance. The other one is that the features are scaled to be roughly the same, because otherwise, when you calculate Euclidean distance, if one dimension is scaled much higher, it's going to dominate the distance. So you don't want that to happen. You want them to be the same. Okay, so you assign, but returning to the algorithm, you first assign it to the closest data centroid, and then you update, you update the centroid. So you've assigned all the data points to their centroids. Now you want to update where those centroids are located. And the way that you do that with Euclidean distance is you literally just take the average of all of the data that has been assigned to a centroid. So if you want to update the first centroid, the first flag, you want to update its location, you take all of the data that was assigned to that flag, to that centroid, and you average it. And the reason why it's so simple is because of Euclidean distance, which is why somebody would pick that because it's that simple, right? You just average it to get the new location, then you return to the second step, right? The location, the centroids have changed their location. So perhaps you want to change your assignments. For a particular data point, maybe originally it was closer to the third centroid than the second centroid. But now that you moved those centroids, it might be closer to the second centroid than the third centroid. So you have to return to the second step and reassign everything. But now if the assignments change, that means the averages change. And so you have to then do the third step. And so you can see why it's naturally an iterative algorithm where you're going back and forth, because changing the assignments changes the averaging, and then changing the to get the new centroids, and then changing the locations of the centroids could change how you assign the data points. So you iterate back and forth until eventually it converges. But what it converges to is not necessarily the best solution, because it depends on how you initialize your model. If you initialize your model differently, it could converge to a different solution. But by and large, my experience is that it usually converges to something pretty good. I mean, if you find one that's better than, if you find one solution that's a little better than the other in terms of the objective function that you're trying to optimize, empirically, they look mostly the same in quality. Is it necessary to visualize the data? It's not necessary to visualize the data. We're going to see a potential. So in order to, if you pick K, if you pick K to be 5, then you can just run the algorithm. You don't need to visualize the data. The problem is that you need to know what K should be. And so when we visualized the data, we got a sense that maybe K is 4. But if you can't visualize the data, how do you pick K? And so we're going to see a technique that, you know, isn't like bulletproof, but it's a common technique that people could use to get a sense of what K should be. But that's going to be later. Okay, so K-means clustering relies on minimizing the Euclidean distance between data points. So to return to an earlier question, what kinds of issues, you know, do we have to assume? What problems might this pose in terms of the results that we get, and how could we fix that? So the key problem is that there might be a problem of scaling of the features. So when you calculate the Euclidean distance, it's, again, think like line of sight distance. If you put a rope between you and the object and stretched it out, how long would that rope be? Well, if you change the meaning of a dimension or the scaling of a dimension, that rope can grow or shrink, right? For example, imagine one of the dimensions is income in dollars, like in the data set we're looking at. That would be a certain amount. But what if you give income in pennies, not dollars, but pennies? So you take the income in dollars and multiply it by 100. It's the same value, right? It's the same information. There's no difference between the information. One is dollars, one is pennies. But the Euclidean distance between two data points is going to change a lot, right? Because one dimension is 100 times larger in one case than the other case. And when you calculate the distance, that's going to show up. And so if you calculate the distance between 2 points, one dimension is, say, age, and the other dimension is income. For example, if you just looked at 2 dimensions, age and income, and you wanted to calculate the distance between 2 people, well, the age goes between, you know, 15 to 95 or something in our data set. So it's you know, 80 plus or minus, you know, 80, the width of the data is 80. Right? The youngest person, the oldest person, there's a difference of 80 in years. The income difference is like something like 10,000, say, to 150,000 or something. So the difference there is, say, $140,000. But Euclidean distance doesn't know units. It doesn't know one is dollars, one is years, right? There's no units when you calculate Euclidean distance. Euclidean distance looks at one dimension and says it differs by about 80, plus or minus, you know, something 80. and the other dimension, it says, has 100,000 difference. And so the dimension, the income dimension, is going to completely dominate. If you look at two different, if you say who's closer to whom, the income is going to be much more important in determining who's closer to who. And age will have very little impact. So you have to get rid of that, assuming that age is just as important as income and the units are arbitrary, you have to get rid of that issue. So there are a few ways to do that. All of them involve scaling your variables. You scale your data so that they all have the same kind of spread. One way to do it is to subtract. So usually they always involve subtracting the mean from the data. I guess in this example on the screen it's not. But one way is to standardize it to make each dimension have mean 0 and standard deviation equal to 1. So that's by far the most common, where you take each dimension and you subtract the mean, and then you divide each dimension by the standard deviation of that dimension. So the standard deviation of income is going to be much larger because the values vary by a lot more. And the standard deviation of your age is going to be much smaller because the values vary much smaller. So when you divide the age by a smaller value, divide the income by a larger value, that scales them so they have about the same scale. So the criteria to pick the distance, usually it's by problem. So there's usually you kind of know it. If you have a bunch of real valued numbers, then usually you'll use Euclidean distance. If your data is, say, categorical or something else, then you would use a more appropriate distance between two categorical variables. If your data is at like a line of text, like a word, you can calculate the distance between two words or how similar they are. But really, that's part of the kind of the process. That's, there's no clear answer. Euclidean distance, if you can use Euclidean distance, usually that's what people will use. Okay, so I guess that's what this block of text is saying. It's the most common, works well. But it's what I'm saying now is, when I say Euclidean distance, that's not a rigorous scientific statement. It's more of a hand-wavy statement. Okay, so we're going to normalize our three variables. Remember, our age, the income of the person, and the claim, how much they want from the insurance company. I think in this one, each one is normalized a little different. I mean, this is arbitrary, how these are normalized. So what I'm showing here is not the correct answer necessarily. This is one way you can do it, but the way this is done is by scaling the age so that it's between 0 and 1. So you subtract the minimum. So you subtract the minimum value and then divide by the range, which basically takes everybody's age and maps it and shrinks it so that it's the same pattern except between 0 and 1. So that's called the min-max scaling method. It's, very sensitive to outliers, so that's an issue. Outliers will kind of affect any scaling. One way you can, I think we might see this later, is to perform functions of your features. For example, rather than scaling the income, scale the log of the income, something like that. But outliers are a big pain too. But k-means kind of assumes that all of that has been taken care of. Okay, so we scale the age. We've scaled the income. I'm not sure if this is the log of the income. Let me check perhaps. Yeah, so you see here, this is the log of the income. So we've scaled the age to be between 0 and 1, and we've scaled the income by calculating its log. So this transformed the data in a way where the dimensions are roughly similar. Age is between 0 and 1. Income is more plus or minus, say, 3. So you might still, subtract the mean and divide by the standard deviation just to get the scaling right. I'm not sure if that's what I don't think that's what we're going to do in this one, but ultimately the key takeaway is that scaling will affect the result of the algorithm. And you want the scaling of each dimension to be roughly the same, so that if you plotted, say, a histogram of the data on each dimension, the spread is roughly the same. That's what's the key thing. So minimax, yeah, so the mean and the standard deviation, usually that's what's done. In fact, I mean, this is just to introduce min-max, but almost always if it's real valued and there are no terrible outliers, what people will do is subtract the mean and divide by the standard deviation, which makes a Gaussian assumption of your data, kind of implicitly. But at the end of the day, the whole point of this is you want the 3 dimensions that we're looking at to be roughly the same in how far they spread. Okay, so the next exercise, let's imagine a situation where, in addition to our original data set, there were a few high income earners who also filed high value claims. So this is getting to what people have already anticipated. What might go wrong with the scaling method, and how might we deal with this? So in this case, we don't have this in the data set, but these data points would be outliers. They would, be very far away from everything else in the data. However, that would significantly impact all the scalings. So the min-max scaling would be impacted. Also, if you subtracted the mean and divided by the standard deviation, that would also be impacted, because perhaps not as much, but the outliers would increase the standard deviation and also increase the mean by a lot. So that could also have a big impact. One way to do that is to delete those data points, which is, if they're very few in number, that might be the first thing to try. But generally, you don't want to delete good data if you don't have to. So another way to do it would be, so here it's talking about dividing by the mean, scaling by the mean and standard deviation, but that would still have some issue. But another way is to perform a function of the data, like to take the log. So already we took the log of the data in the previous one. So this is showing a different scaling. I think I'm not sure exactly what was done here off the top to remember, but at the end, the outliers somehow need to be not skew things too badly. And so one way to do that is to take logs of your data so that they aren't as big of an outlier. That's often done, is to take the log of your data if there are tails. I think in the previous lecture, we also saw that, where we looked at the violin plots, and one of them was the income. And we took the log of that, and it was very skewed, but then we took the log and it kind of made it look more Gaussian. Yeah, so it's useful to check the data, to do some kind of histograms of the data to see if it looks roughly normal, or to see what the outliers look like before just scaling them. And then you can do functions, to make it roughly more Gaussian, like take square roots or to take the log. Okay, so now I spent some time kind of going over the pre-processing, because it is crucial that your data is processed in a good way before you use k-means. Otherwise, it's going to happen where one dimension is going to completely dominate the way that it's clustered, and it will ignore information from the other dimensions if one dimension is scaled much larger than the others. But now we're assuming that we have good scaling for our data, so we can look at the algorithm in action. So first, by looking at the data, we're going to kind of assume that we have 4 groups, and those can be given names based on where they fall in the feature space and our interpretation of what the features mean. So now let's look at how we can cluster this with k-means. So we aren't doing the math necessarily. We aren't showing what the math function is that we're trying to minimize. We aren't doing derivatives and calculating the algorithm to show that this is the correct answer. But at the end of that whole process, this is the algorithm that we get. This is what the procedure that you run. And that procedure can be shown to optimize a certain math function and converge in all of this. So the first step, so here's our data. I believe in this example, we're just clustering based off of incoming claims. We're ignoring the age for now in this example. So we only have 2 dimensions in this clustering example. So we've initialized our 4 clusters, our 4 centroids, and they each has a color, and this is the location of the initialization. So it's not necessarily the best initialization because one of them is far away from the data, but this is a hypothetical initialization. We then assign, here it's the word classify is being used, but we're not really doing classification. We're assigning each of these data points to the closest centroid. So this data point is closest to the red centroid, so it will be colored red, for visualization purposes. It's assigned to this data point. So I guess I can show that result now. So here was the starting out. No, this is not where we start out. This is where we start out. This is where we start out. We then do the assignment, and so that's what this is showing. The color of each of those data points is indicating which of the clusters it was assigned to. So all these bluish data points were assigned to this centroid here. All of these green data points were assigned to this centroid. All of these light blue data points, you can't see the centroid, but it's right there. And the red data points are assigned here. Okay, so this is how they were assigned based off of how close. So anything that's red was closest to this data point. Anything that's purplish was closest to this data point, and so on. That's step 2, if you remember, of the algorithm. Step 3 then is to update these 4 centroids. And the way that we do that is by taking the averages. So to update the red centroid, we take all of the data that was assigned to the red centroid, so all of these red data points, and calculate the average value of them. And that gives you this point. So that's why the red point moved from here, the initialization, to here. Yeah, so you're seeing a good visualization there. To here, the update, right? So all the average, if you took all these data points and averaged them together, that's the location. So that's the update. Green, you took all these green points and averaged them together, that would be the update. So it moved up a little bit, it moved from here to here. Light blue, I believe it started out here, and then the average, you see updates there because there are a few data points down here. So it moved from about here to here. And then finally, this one didn't move too much, it moved like right there. So that's the first iteration of the algorithm. You assigned everything, and then you updated. That's one iteration. So if we have a skewed distribution with no clear correlation, so k-means actually doesn't really worry about correlation. What do I mean? So kind of think from the perspective of this algorithm. Imagine you had this data set here on the left, but the data somehow got rotated like that. So the relation of all the data points to each other was exactly the same, but it just was rotated a little bit like that. You would be changing the correlations between the data. So this dimension is still claims, this dimension is still income, but now imagine instead of this data set, you had the same data set, but rotated on an angle like that. So the correlation has changed between claim and income, but you've changed the correlation structure of the data. K-means would not have a clue that you did anything, if you think about it, right? The Euclidean distance is the same if you rotated everything. The distance is the same, and then the average is the same. So from the perspective of K-means, using Euclidean distance, it wouldn't change anything. So it's kind of invariant to correlations. If instead of Euclidean distance, you used Manhattan distance, which is the L1 distance. So for example, the distance of this point to this point in Euclidean distance is the length of this line. The distance of this point to this point in the Manhattan distance is this length along this dimension plus this length along this dimension. So the Manhattan distance is this plus this. If you rotate the data, that distance will change because the dimensions are staying the same. You're still moving this direction and this direction only, but they're kind of rotating around each other, right? So Euclidean distance is the one unique one where it's invariant. It doesn't change depending on the correlation structure, but using other distance measures, you would maybe have to worry about that. So to what extent do you have to run the algorithm to get the final clusters? So if you mean like how long do you run it? So you keep basically, this is one iteration, step 2, step 3. Now these have changed, so you go back here and reassign. So basically you run this process until the locations stop changing. And the algorithm will tell you because it'll notice that nothing has changed, and then it terminates. So in general, that doesn't take too many iterations in practice. I mean, it could take, can take 10, 20, 30. I mean, it's not going to run for thousands of iterations usually before it converges. Okay, so that's one iteration of the algorithm. You assign and then you update. Now the next step is to run a second iteration. So we can't, it's, you know, we aren't seeing all this on one screen, but notice that the locations of the centroids have changed. Red is now there. Originally it was there, but then it changed there. So it's right there. And now the assignments have changed. Notice here, for example, you get red right here. Originally you had light blue there, because originally the red dot was farther away over here, but now the red dot has moved closer to these points. And suddenly these points are now closer to the red dot than the blue dot, right? So the assignment has changed. Now suddenly these points get assigned to the red cluster. You get some additional changes. So, you know, there's less darker blue to here and more green because this one moved up. Notice it moved up from about here to here. So now suddenly some of these purple ones are closer to the green than they are to this blue. Whereas originally they were closer to the blue than the green, now they're closer to the green. And so you can see there's more green up here. And then you update the centroids. So you've changed the assignment. So now the average of the red changes. If you notice it moved a little bit to the left. This green one, I believe, probably moved a little bit up. This blue one is very obvious. It moved much farther to the right. And this one didn't change too much. Moved a little bit back to the center because it lost some points over here. But the blue one still made a big change because now suddenly there are many points here that are dark blue and only a few points here that are dark blue. So the average center of mass moves. Okay. So now we've, this is basically, you know, that's k-means. You keep running that until things stop changing. And at the end, you get a bunch of data points assigned to the red cluster, some data points assigned to the blue cluster, the green cluster, the purple cluster, and so on. And then the output of the algorithm is, you know, this data point was assigned to this cluster, basically. It tells you which cluster it belongs to. And also you get the centroids as well if you want to use those. Okay, so the next we'll discuss initialization. So initialization is important for k-means, very important. Here we implemented a crude initialization by just randomly picking points. However, it can be sensitive. So if you change the initialization, it could give you pretty different results. So in Python, if you use the k-means package, there's this thing called k-means plus plus. The plus plus indicates that a initialization technique is used to help with this, and it's kind of interesting. It's fairly straightforward, but we can talk through what it does to make sure that the data points are good initializations. So if you think, what do you want as an initialization? You want two things. If you think of your initialization, right, what do you want? You want two things. You want your initialized point to be in the data somehow, right? You don't want it to be in the middle of nowhere. You want it to be kind of close to the data. And you also want the centroids to be far apart from each other. So you don't want this red point to be initialized right next to the blue point. You want them to be far apart, so that that'll help with the convergence to a good solution. If you put this red point over here next to the blue point, you still would get something at the end of the day for this data set that looks like this, because it's a very simple data set, low dimensions. What would happen is you just have to run more iterations, most likely. So, you know, this is a very specific, but most likely if this red point were initialized right here instead, right? This point would probably get dragged over here, and then maybe the red point would get dragged down there, and then suddenly this would be red and this would be light blue, right? But eventually things get sorted out. But in high dimensions with complex data, you can get some very bad local optimal solutions, so you don't want that. So you care about the initialization. So here's what k-means plus plus does to initialize. First, it selects the first, what it does is it initializes each centroid to be equal to one of the data points in the data set. That way you can be pretty confident that the centroid is in the location of the data. Then each centroid is initialized to be one of the data points in the data set, but then it wants to do it so that it picks it so that the k data points that it picks are far away from each other. And so this is the algorithm. First, it picks the first centroid at random from the data. It's the first one. This is all initialization. So the first one, you know, there's nothing else there, so it can pick anyone it wants. The next thing it does then is it calculates how far is each data point to that centroid. And it randomly chooses the second centroid to be a data point far away from that first centroid based off of a probability distribution. So data that's you know, far away has higher probability of being picked. Data that's closer has lower probability, and it randomly picks. And then it does the same thing for the third centroid. It calculates, actually doesn't say exactly precisely what it does, but I think it calculates the distance to the closest of the previous two centroids between each data point, and then constructs a distribution on the data, and then picks a data point, the third centroid, based off of that distribution. So data points that are far away from the previous two centroids have a higher chance of being picked to be the third centroid, and so on. So it's a good a way of initializing k-means so that you can be more confident that you're going to get a good clustering solution at the end. That's not a bad local optimal solution. It didn't converge to something bad. Okay, so we run that on this data set, and we get this clustering at the end of the day. This is the clustering that we get. You know, all these green points are grouped together, the blue points are grouped together, and red points and the light blue points are all grouped together. This is based off of incoming claims. It looks like these have been have been standardized in some way. So that's the algorithm. The next question is, how do we pick the best value for k? So in this simple example, what we did was we visualized the data, and it looked like 4 groups were in our data set. There were 4 clusters. If you can do that, if you can use your eyes with plots, that's the best way. I mean, that's a really good way to do it. But it's hard to do that when the data is multidimensional or complex. So for example, if your data is categorical or some other type and you aren't using Euclidean distance, how do you visualize the clustering? So how could you, so this is kind of a thought experiment plus a method for picking K. How might you go about constructing a quantitative method, meaning you aren't just looking at it with your eye, but you're using numbers to try to help you pick the best value of K? So the first thing to notice is that as you, what is the objective function? So we didn't write the objective function out, but the thing you're trying to minimize is the sum of the squared distances between each data point and its cluster. So what the objective looks like is you have every data point is assigned to a cluster, and there's a distance of how far that data point is to its own cluster. You get that number for every data point and you sum it up. That's what we're trying to minimize with k-means. But if you think about it, as you increase k and look at that objective function, that math function that you're trying to optimize, as you increase k, you can always make that number be smaller. So you can always make that distances be smaller. And in the most extreme case, imagine that you have n data points. Imagine you have 1,000 data points and you set k to be equal to 1,000. You can make each data point its own cluster and each centroid to be equal to that data point, in which case the distance of a data point to its own cluster is 0. So the more clusters you make, the smaller you can make this distance be, until you get to the point where every data point is its own unique cluster and the distance of a data point to itself is 0. So you can't, the point is that, you can't just increase k and look at the objective function and hope to pick k when that value is smallest, because it should monotonically be getting smaller. It should never get bigger as k increases. So what is another way? So I'm going to describe a way called the elbow method for picking it. The idea, I think I'm going to use words to describe the idea, but it's pretty straightforward. Maybe I'll talk to this picture. So this is the data we want to cluster. So there's a missing paragraph. I'm not sure maybe where the paragraph, I didn't update this, but it might have been added. Yeah, so that's yeah, right here. Or maybe that's missing for you, I'm not sure. Okay, so this is the elbow method in a nutshell. So imagine that you had this data and you clustered it into 2 clusters. You would get something like, everything, maybe these 2 are grouped together and then these 2 are grouped together or something. And then you calculated the objective function. It would be pretty bad, because if you grouped, for example, all this data together, the centroid would be something like right here. And so every data point would be very far away from its centroid. But you only have 2 clusters, so that's why they're grouped together. And then you group everything here into the second cluster, the centroid might be right here. So everything's far away from the centroid, but you only have 2 clusters, so that's where it ends up being. So the objective would be very bad. Everything would be very far away from the centroid. Then imagine you add a 3rd cluster. Now suddenly, maybe that 3rd cluster, breaks it up. You would imagine that the distances would be much, much smaller. The objective function would have a huge improvement, because now suddenly your data wants 4 clusters and you gave it a 3rd cluster, and so you see a huge improvement. And then imagine you add a 4th cluster. Again, your data, if it wants 4 clusters, you would see a huge improvement in the objective function after 4 clusters. And then from 5, 6, and 7, and so on, you would always see improvements because you would be partitioning and chopping up your data into smaller and smaller bits. But the marginal improvement would be less. Going from 4 to 5 clusters would not be as big a deal as going from 3 to 4 clusters. So we always cluster around one point. So you can always make it more complicated. You could cluster around other things, but for this one, we're clustering at a point. Okay, so this one, how do we get this to be read? So using Euclidean distance, I guess that's going to be a default, a defect. There are methods that are more that use probabilistic approaches, maybe more advanced, like things called Gaussian mixture models, which are beyond the scope of this lecture, but Gaussian mixture models would say learn 4 Gaussians. Don't learn 4 points and then use Euclidean distance. Learn 4 Gaussians. And then you could learn 1 Gaussian where this is the mean and the covariance looks like this. And a second Gaussian that kind of looks like this, a third Gaussian that looks like this, and the fourth that looks like this. In that case, because of the covariance structure for the Gaussian that you learned, it would want this to be part of this cluster because of the covariance structure. But that model is very different from the one we're talking about here. I mean, in terms of the algorithm, what it looks like. But there's this Gaussian mixture models, they're called. So that would be like a next level clustering model to look into. Okay, so we run this elbow method, and we get something like this. So with one cluster, there's actually not an algorithm, it's just the mean of all the data. And this is the sum of the squared distances to that mean of all the data. So it's very large. Everything is far away from its mean, from the mean of the entire data set. When you add the second cluster, this is the sum of the squared distances of each data point to its own cluster. You get a huge drop, a huge improvement, because you've chopped the data up into 2 regions, right? And that's helped cluster it a lot. 2 to 3, you get a certain improvement. 3 to 4, you get another improvement. So when you look at it, it's very obvious you need at least 3 clusters. You're always, as you introduce more and more clusters, you're always getting a better and better objective because you're always making everything closer and closer to its own centroid. But the improvement, the marginal improvement drops after 3, maybe 4. So if you were just eyeballing, if you were just doing this, you might choose 3 and not 4. So, it's not a perfect method because I think 4 is definitely a better answer than 3 for this data set. But you can see this is kind of the rough, method. You might even pick 5 to be a bit cautious. But looking at this function, that after 5, there's no point because the marginal improvement is not getting better, drastically better. So yeah, I would say diminishing returns, yeah, it would be a good way to think about it. So why not use 10 clusters if that's better? The reason you could do 10 clusters, what you would then get is you get this data set chopped up into 10 different regions. For some problems, that might be okay. So it's not necessarily the case that you have to have 4 for this data set. For example, and I think I have time, so I can, we might end a little early, but I can kind of give an example. Imagine that you had a bunch of tasks that you wanted to assign to people. Each of these dots represents a task, like a job somebody has to do. And this information represents information about that task. And you want to assign the tasks to each person. You want to assign tasks that are similar because it makes their life easier. If they see kind of the same thing over and over again, maybe it makes it so that they can complete the task quicker and then move on to something else. You can imagine that. Now imagine that you have 10 people that you want to assign these tasks to. Well, then you have 10 clusters. And so you can cluster your data and make it so that each person gets one cluster of the data, and all those data points are very similar. In that case, you don't care about chopping this up into different groups. You don't care that necessarily this is one unit. You could chop it up into 3 units, and that's fine. So in that case, that would be an instance where you know what K is in advance. You know you want K to be 10. If the problem is more like you want a big picture idea of how many different groups are there within your data set. So for example, you might look at this and say, I want my algorithm to tell me there are about 4 groups in this data set. Using this method and picking the best value would not be good, because the larger you make K, the better the value is going to get. If you make it 11 or 12, it's still going to get better. So using that number is not tell you kind of intrinsically how many groups there are in your data. If that's something that matters to you, if you care about, you would imagine for this data set, there are 4 different types of people, and you might want to know what those 4 types are. And you might then want to be able to group each person based off of what type they are. And so you might want to know that there are 4 different units of how the data breaks apart. So it's more of like this, model-driven exploratory data analysis. Again, you want to understand something about your data and how it's structured, but you want a model to help guide that for you rather than just plotting histograms and violin plots and things like that. Can you use it to predict? So you can build it. Currently, we don't have any labels, so we have no way of predicting anything here. You can use this to help you predict data. It's a bit more complicated than I think maybe at least today that I've prepared us to talk about. But one way is, for example, in a naive Bayes classifier. So imagine that instead of k-means, there are probabilistic versions of k-means where each cluster is a distribution instead of just a centroid. And you might use that to learn the distribution that we talked about previously for naive Bayes. That's one very powerful way of how you could use this, but that's pretty far from what we've been discussing, so it might not make any sense. But in general, the clustering algorithms are not thought of as helping you make predictions. If you just think of, I want to use a clustering algorithm for a problem, you're not wanting to make predictions about people. You're wanting to understand your data, and then maybe you learn a cluster, and then the human goes and tries to analyze or interpret that cluster themselves. And then you could make predictions based off of what cluster. If you say anybody in this cluster, I want to flag it for a human to analyze it more closely. That would be like making a prediction in a sense, but it's different. It's not really supervised learning, so it's a subtle difference. Yeah, so really, yeah, we want to get clusters, and then the human is going to kind of come in and interpret these clusters, give meaning to them in some way. Whereas if you think of the classification problem, you have an answer and you're trying to predict the answer. You're not predicting the cluster, you're predicting the answer, and there's nothing to interpret. You just make a prediction. This is what I think is going to happen. Okay. So I think exercise 8 is now just analyzing kind of the results of k-means. So we can give interpretations. I mean, of course, with this simple of data, we could have used our eyes to do this. But again, you can't necessarily know what's going on with the eye, but when you get this data. But at the end, what you would get is these centroids, right? This would be the output. You get these 4 centroids and the assignments. You would then look at this location, you would plot it or something, you would look at the values, and you would say, this is low income, high claims. So this cluster, the centroid is capturing people with low income and high claims, and you would get some information. You would also know how common that is. You would know that only a certain fraction of your data is in this cluster. You'd also get a cluster that says high income, low claims, and then you would know a certain fraction of those people are there. You would get middle income, middle claims, and you would get whatever this is, higher income, higher claims. So you would get these clusters, and you would then be able to give some sort of a meaning. So I would think k-means is, as we're talking about it today, is more for EDA than predicting for the purpose of this. It's used in other ways as well. For example, if you have continuous data and you want to discretize it, which is a whole process that we haven't talked about. Okay, so we can, go back and look at the clusters and kind of interpret what's going on. And we can, for example, say any data point that's in the low income, high claim cluster, we should look a bit closer at those, because that's where the fraud might be. If somebody wants you to give them 3 times the amount of money that they make in 1 year, there's a huge incentive, even if it's still low probability maybe, but there is an incentive for them to want to perhaps make a fraudulent claim, because it would be giving them 3 times more money than they make in a whole year, right? So that's maybe a bit more suspicious. Again, though, it's, you look at the data and I'm sure you realize that actually it's still only a small fraction of people who do that who are being fraudulent. So you want to always be kind of aware of what's going on. Maybe just look a little bit closer at it, but you don't immediately say this is a fraud, right? You have to look a little bit closer. Perhaps you have to call up the person and ask them questions or get a little bit more information from them, just to verify, and that additional information could then give you the information that you need to know whether it's a fraud or not. Whereas other claims you might want to automate, because you can't have a human maybe talking to everybody. It's too much work. Could we cluster the data and then use a model for each cluster? For example, have different binary trees. So that's possible. I think people have done that. It's, for example, you cluster first cluster the data and then learn a classifier separately for each cluster. I don't know of a very famous model that does that, but as a framework, that would not be considered kind of the intro level thing, but it's definitely something you could do that would make sense and might work, where you, instead of building your classifier on the entire data set, for example, a logistic regression, instead of building logistic regression on the entire data set all at once, you cluster your data into 4 groups and then build 4 different logistic regression models for one for each group. And then to classify a data point, you first find its group and then use the classifier for that group. What would that allow you to do? Well, logistic regression, is a linear classifier. You just draw a line, and then if it's on one side, it's one class. If it's on the other side, it's in the other class. But a lot of data sets don't work that way. And so what that could do is, in each group, you have a linear decision, but then the groups are different, so they can kind of construct something that's not linear. It's maybe curved or something. So that could help out. Okay, so I think to conclude, or maybe we have some potential shortcomings. So k-means gives more weight to larger clusters than smaller clusters. So that's an issue where the larger clusters could dominate the results that you get. It doesn't necessarily converge uniformly or quickly if you have a large data set with high dimensions, but that's not so much of a key issue. I wouldn't worry so much about that. Because when you say converge, so there are some issues where it could take a long time to converge, but after a certain point, the result's really good. And really, it's just making very, very small changes that aren't really affecting the performance. So often with k-means, you might not even run it until it finally converges. You might say, run it until the change in the objective function is small and then stop. And then finally, outliers. This is the key. I would say. This is the most important issue. This is the second most important issue. And this is a distant third. But by far the most important issue is considering whether or not you have outliers, because that can heavily impact what you learn. Okay, so can we use k-means to analyze a single feature? So you can do k-means when you have one-dimensional data. It's if you only have one-dimensional data, it's easier to visualize it. So k-means is really useful as an automated process. I think, you know, when you have even more than the 3 dimensions we look at here, if you have like 10 dimensions, how do you can't even visualize it. You can't even look at it. So how do you do it? K-means can help you automatically do that. With one dimension, then you can kind of just visualize it with histograms and things like that, and perhaps manually do it. So k-means and SVM are different. K-means is clustering, SVM is classification. So they're pretty different in what they're doing. How do you evaluate the performance? So the performance usually is downstream. So if it's an EDA problem, you just see whether you learned any insights from the process, the clustering process. If the answer is yes, then you know it worked. If the answer is no, then you have to ask whether you didn't get insights because there are no insights in the data, or because maybe you need to change K, or maybe you need to change the distance from Euclidean to a different distance. So usually it's very subjective. The way that you evaluate the performance is often very subjective. Okay, so I guess to conclude, probably end about 10 minutes early. In this case, we introduced the concept of unsupervised learning and clustering techniques. Specifically, we talked about k-means and how it works, what it does. We introduced the concept of k-means. We talked about the algorithm for learning it. We didn't get into the math of why that algorithm is correct, but there is a derivation, a mathematical, straightforward derivation that shows that that's the correct algorithm for k-means if you want to minimize the Euclidean distance. We talked about some of the pitfalls and some of the drawbacks, outliers, data with different densities, and also the fact that Euclidean distance might not be appropriate. Scaling the data is very important. Sorry, I'm not doing it in order, but scaling of the data is very important so that each of your features has roughly the same scaling. That way, one feature won't dominate the others. But Euclidean distance is the one we discussed. There are others that you can use. But in general, clustering is a powerful technique. It's very useful. It's one of the fundamental unsupervised learning techniques. K-means is the most famous by far of all the clustering algorithms for determining what patterns there are in your data set. There are developments of k-means and other ways of doing clustering. T-SNE is a very advanced technique that tries to map your data. So it's too much to go into, but sometimes your data is very nonlinear, or you need to map it or modify it or morph it in some way before you do the clustering. T-SNE is one way to do that. Something called spectral clustering is another way to do that, where you don't do clustering on your original data set, you morph it or modify it in some way, then do k-means clustering. So somebody raised an issue about it should be in the red cluster and said that would fix that problem potentially. Then there are probabilistic ways like using Gaussian distributions rather than just Euclidean distance, which can account for the correlation within each cluster. So each cluster might have a different correlation structure that can capture that and would allow you to cluster based off of that information. But I guess to wrap up, I could also say that, as you see in the code, I mean, this is really standard technology at this point. So they're built-in functions for k-means, T-SNE, Gaussian mixture models, and so on, and other ways of doing clustering. A lot of work has been done on this. So I would say most of the built-in functions that you see will be high quality, and you can kind of work with them without having to worry about whether they're taking into consideration all the pitfalls, other than pre-processing your data. So to finally wrap up, if you call k-means, it's going to assume that the data that you want to cluster is actually the data you want to cluster. It's not going to pre-process it for you necessarily, although I'm sure people put in those bells and whistles. You have to make sure that your data is processed properly before you ever run any of these clustering algorithms. Otherwise, the results could be just really bad. How many, how much data do you need? So in general, you want each cluster to have many more data points than you have dimensions, right? So if you have 4 clusters and your data is 2-dimensional, then to learn a 2-dimensional cluster, you need maybe rule of 10. I think I saw that somewhere. 10 times as many data points as dimensions. So say 20 data points per cluster, and then 4 clusters, so 80 data points could be roughly okay. But in general, you want the number of data points to relate to the number of dimensions by like 10 times or something like that. And that's based off cluster, not the entire data set, but each cluster has a certain number of data points that you need to appropriately learn the number of dimensions. So it's a hand-wavy answer, but when you have high dimensions, you need lots of more data. And when you have larger clusters, you also need a lot more data. So there's 2 dimensions there. As the dimensionality increases and as the cluster number increases, you need more data. So it can blow up pretty quick. If you have high dimensional data and you want to learn a lot of clusters, you're going to need a ton of data because it's blowing up in those two values. Okay, so I think that's everything. So when you have many, so I can answer this last question quickly. So when you have very many points, there are stochastic methods for clustering. That's a bit next step, but you can either iterate through all 100,000 points, and that might take a very long time, but there are speed ups. If this is what you're asking, there are speed ups for how you can subsample in creative ways to speed things up. So I think I'll end there.
Okay, thank you so much, Professor John, for the amazing lectures. And remember, guys, building models is something that you learn by doing, not just observing. So hands on those models. And we have finished this part of the day, and now it's time for lunch. After that, please go to your respective team meetings. Don't miss them. See you in the afternoon for our extra session about CNN, and happy lunch. Thank you again, Professor John. It was so great to have you here with us.
Great, thank you. Thanks, bye everybody.
Bye.